What if I told you that the Headlines app we built before can also be made to run on the web, and it'll look exactly like a native app? And to achieve that, we would only need to do a few platform level tweaks in code and almost nothing in the UI code. Sounds too good to be true, right? But let's make that happen. In this episode, let's make a web application in Rust that runs in your browser but feels like a native app. If you're new here, you can find the previous episode in the description. Hey, welcome to another one. So just to recap our journey so far, as part of this series, we had started by creating a command line app for reading news articles. We then extracted and created an API client library out of it, and then we used that to create a native GUI app using the eGUI crate. And continuing with that, we're taking it a step further and trying to port our application to also run it within a web browser. And to make this happen, we're going to have to compile our Rust code into something that can be run in the browser. And one technology that makes it happen is called WebAssembly. So here are some of the changes that we're going to do. First, we're going to add a dedicated fetch API in the news API crate when we are running headlines in the browser. Then we'll convert headlines, which is currently a binary crate, to a library crate, and we'll expose it as a dynamic library, which will help us in creating a WASM module out of it. And then we'll add a few conditional compilation checks to use correct APIs when running on the web platform. Then we'll switch to using eGUI's built-in persistent APIs, as it covers both the native and web platform. And finally, I'll provide the solution for implementing the refresh button handler that we left as an exercise in the previous video. So yeah, I'm super stoked to be adding these changes. Now, in order for everything to make sense when we start with our implementation, let's get a bird's eye overview of WebAssembly. I'm going to start by first talking about what WebAssembly is not, as to cut down any held assumptions that you might have read elsewhere. So WebAssembly is not a programming language, it's not a compiler, and it's not even a virtual machine. What WebAssembly is that it is a standard specification for a set of instructions called WebAssembly bytecode, and also a virtual machine spec that can run that instruction set. The specification is a joint effort by major browser vendors such as Google, Apple, Samsung, and Mozilla. With this definition, however, it's not so apparent how one can use WebAssembly. You obviously won't write the instruction set by hand because it would be impractical, but the word assembly in its name gives us an idea that it is meant to be used as a compilation target. So usually you will have programming languages that will compile your code down to WebAssembly bytecode as a module. One can then instantiate or run these modules within a WebAssembly virtual machine. Now, there are several implementations of virtual machines, aka WASM runtimes, such as Live, Lucet, and Wasmer. These, however, are independent runtimes. The runtime that we are interested in for this video is the one found in web browsers. For example, Firefox's SpiderMonkey engine, which also implements the virtual machine spec. And that means Firefox can run WebAssembly module. Same is the case with other browsers as well. But you might wonder, how do we generate our WebAssembly module in the first place? Well, Rust can compile code down to WebAssembly thanks to LLVM, which is the low-level code generator for Rust, and it implements WebAssembly as one of its backend targets. At the moment, only shared or dynamic Rust libraries are supported to be run in the browser, so we'll need to expose and compile our Headlines app as a dynamic library. Also, there are a few differences one needs to take care when running code in a browser. A browser is a sandboxed environment, which means that it cannot access native low-level operating system APIs such as the TCP stream object or file APIs. For example, for making HTTP requests, we cannot use Rust's default standard library as it calls into native OS abstractions beneath. Instead, we'll need to use the browser's own fetch API to make HTTP requests. And there are other similar platform-specific changes that we'll have to do. We'll uncover those as we implement our code. So this was a very brief overview, but should be enough for us to understand the implementation ahead. So let's go back to our project, and under news API in lib.rs, let's start by adding a fetch web method, which will only be available in a browser environment. This will have the same return type. And since we only want to include this when running on the web, we're going to add a conditional flag here, and we're going to say if the target architecture is wasm32, which is an identifier for the WebAssembly target. So if this is the case, we want to include this function in the compiled library. Now within fetch, we'll do the same thing as we did in the fetch async method, except we'll use a crate called recwasm, which works very similar to how the request crate works, except that it exposes the fetch API from the JavaScript browser environment, which we'll use to make HTTP request to top headlines endpoint when running in a browser. So let's do that. So let's add recwasm as a dependency, and similar to how we have the conditional flag here, we'll also do a conditional import, because this is only meant to be included in a browser environment. So we can import recwasm conditionally by using target within single quotes. We will write the same conditional expression, and then we'll finish that with the dependencies key. So this should work now. So to test if the build works on a wasm32 architecture, let's quickly type a to-do macro here so that we can compile our code. And in order to build this, I'm going to pass in the wasm target triplet. And hey, this works. So then we're going to do the same steps in the fetch async method. And this time we'll use the recwasm crate to create our request object. We're going to pass the URL and an authorization header for the API key. And then the rest of the code is same as before. So with that implemented, let's try to build this again for wasm, and this works. So now that we have a fetch web method, it's time to make some changes to the headlines crate, and we'll have to expose headlines as a dynamic library and provide a top level function which we can then call in an HTML file, which we'll create later. So in order to convert the headlines crate into a library, I'm going to add a lib.rs file, and I'm going to move the entire API from here and put it in lib.rs. And then since headlines is now being treated as a library crate, we'll move the mod declaration from main.rs to lib.rs, and this should fix the headlines import error. So then let's also fix the main rs import. I'm going to use headlines here, and we're getting an error for headlines being private, because even though we have the mod headlines declared as a module, but to main.rs it appears that headlines is coming from a third-party library. So to fix that, we're going to prefix our use with pub so we can expose headlines back in main. And this should fix that. So then let's also import the native options and the other APIs. So with those changes, we should be able to compile the whole project to wasm. And looks like we still have an error here. And the reason we have this error is because cargo build is trying to also build the main.rs binary with the wasm target, but these APIs don't exist on the wasm target. So to fix that, we'll need to pass the lib flag to tell cargo that we want to build a package, and for the package we'll specify it with the p flag and the name of the package, and let's try to build that, and this works. So with this refactor, we will still have the desktop app running, as you can see, and now it's time to add a function in lib.rs to expose it in the wasm module. So I'm going to define a public function called mainWeb, as this will act as the entry point for our app in the browser. And to expose this function to web, we'll need to annotate it with an attribute called wasm-bindgen. Now this is a macro that comes from the wasm-bindgen crate, which is exposed to us from the eFrame crate. And this is only available in the wasm platform, so we're going to have to conditionally import here. So let's do that. And since this API is only available on the wasm platform, we have the config attribute. So we'll put this on main web as well. Now, wasm-bindgen is a bindings generator library, and it does a lot of heavy lifting of bridging the differences in type abstractions between JavaScript and Rust code at the lower levels. It does important byte level conversions between types and exposes JavaScript APIs to Rust side and Rust APIs to JavaScript side. Now, how that happens is a deep rabbit hole for another video. So with the function exposed, let's initialize headlines like we did in main. I'm going to do headlines.new. And this time, instead of using run native, we'll use the start web function, and this will take in a canvas ID as a param, which is a string, and a heap allocated instance of our app. So I'm going to pass that, and this canvas ID is going to be passed to the main web function, and this will be called from the HTML page that we create, where we'll have a canvas element and we'll pass the ID of that canvas element to this function. So let's check if all of this still builds. So just like how Run Native needs an OpenGL context in desktop, the HTML Canvas API also provides us with a rendering context, and that's why Start Web needs a Canvas ID so that it can get the rendering context from the Canvas API. And looks like our app successfully builds. So then let's also add logging implementations, as it would be handy to log things in the developer console. And for that, we'll be using the tracing wasm crate, which redirects any logs from our app to the developer console in a browser. So I'm going to conditionally import that as well in the headlines crate, and I'm going to type tracing wasm, and this is going to be 0.2. And initializing tracing wasm is simple. We can just type tracing wasm and call set as global default function, and let's check that, and it builds. Now the one last step we are missing here is to declare the library type of the headlines crate to produce a shared library. So under lib section, I'm going to define a key whose value is going to be cdylib, and this will instruct Cargo to generate a shared object for our library. And the second mandatory library type we're going to need is rlib, so that our app still works on the native platform, because Rust uses static libraries by default. So with that change, let's try to build this again. And if I list the contents of target wasm32 release directory, you can see that we have our wasm module being generated. So the next step is to use the wasm module and load it from an HTML page. So let's create a directory called web app, and within that I'm going to create an index.html file, and let's quickly fill in the contents of the page. So within the body, we have defined our canvas element with the ID of app. And then we have a script tag, which imports a file called headlines.js, which doesn't exist yet. We're going to create that in a moment. And then we have another script tag, which calls a function called wasm-bindgen, and this imports another wasm module. This is also going to be generated in a moment. And the wasm-bindgen function returns a promise. So we chain it with then, and in case the promise resolves, we call the onWasm function, which is defined here. And if the promise is rejected, we then const log it to the developer console. So within onWasm loaded, we call the main web function from the wasm-bindgen module, and then pass in the ID of the canvas, which is app in this case. Now these two files is going to be generated by a helper tool from the wasm-bindgen project. So what headlines.js does is that it gives us a convenient wasm-bindgen module, which abstracts all of the bidirectional communication between Rust and JavaScript side. So these two files will be generated from the wasm-bindgen CLI, and every time we need to make changes to this code, we'll need to keep these files updated. So let's also create a script that will orchestrate things for us. So I'm going to create a script called start web. And first, I'm going to add a build command for headlines crate for the wasm target. And then we are using the wasm-bindgen CLI tool to pass the generated wasm module, and we're giving it an output directory, which is web app in this case. And we are also passing the no modules flag, which means that we don't want ES style wasm module imports. And since we are not using TypeScript, so there's also the no TypeScript flag. So once these files are generated, we can cd into web app, and then we'll serve our index.html using a package called basic HTTP server. Now some of these packages such as basic HTTP server and wasm-bindgen won't be available, so let's also create a script which installs these for us. So I'm going to define a setup web script, and this will have the following contents. So here we are adding the wasm32 target using rustup, and then we install the wasm-bindgen CLI, and then we also update the wasm-bindgen dependency because eFrame depends on that, and both of them needs to be in sync for the generated APIs to match. And finally, we install the basic HTTP server if it isn't installed. So then let's make both of these scripts executable, and then let's try to invoke the start web script. And looks like the wasm-bindgen CLI failed generating the module for us. So after a bit of debugging and incrementally commenting out the code, I figured out that the issue is with headlines using the fetch news API, which calls the native operating system's networking APIs. So to fix this, we want to use the browser's fetch API, which is supported in the browser. So what I'm going to do is I'm going to conditionally compile this section so that we don't include this code when we are running on the web. And for the case when the target architecture is a WASM platform, we'll then need to add similar code as we do here. And also notice the fact that we also don't have thread access within a web platform. And here we're going to add web platform specific code that performs the same as in this code. So we're going to need a replacement for thread and fetch news since they don't exist on the web platform. So for the thread spawn, we can use the setTimeout API. And to use that, we have a crate called glue timers that provides us with an intuitive APIs for setTimeout and setInterval calls from the browser API. So we have a replacement for thread spawn here, which is setTimeout, but we have two branches here. The first branch is something we can handle with setTimeout, but in case of the else branch, which is a loop here, setTimeout won't work in this case, and we can't even use the loop in the WASM specific code because it would just lock up the JavaScript main thread. So instead, we'll use the setInterval API from the same glue timers crate and use that to check messages on the AppRx channel. So let's do that. So first, I'm going to create the timeout instance, and let's put 10 milliseconds since we want this to happen immediately. And the second param takes in a closure, so we're going to create a closure, and then we'll end the timeout call with the forget method. Because if you don't do that, the timeout object instantiated here will deallocate itself when it goes out of the scope. So then within timeout, we'll create a WASM specific fetch news method. So I'm going to call it fetch web. And to this, we'll have to pass the clones of the API key and newsTX. So let's do that. And we're getting an error saying API key is no longer accessible because it was moved with the spawn of this thread. So let's move both of these lines at the top. Now this function doesn't exist, so let's create that. I'm going to simply copy this and conditionally compile this as well. Let's modify the params since we're taking clones of these. And within this helper, we're calling the news API's fetch method. So instead of this, we're going to call fetch web, which we have defined here in the news API crate. And this makes request using the recwasm crate. So let's try to compile this once again. And we have a type mismatch error here from the return type of fetch web, because if you take a look at the definition, it's an async function. And in order to execute an async function, we'll need to suffix it with the await keyword. And then it can return us a result as a response. Now, since we have added await, we'll need to prefix this method with async, because await can only be called in async functions. So let's try to build that again. And this time it works. And if you take a look within the web app directory, we have the headlines.js being generated and also the WASM module. And if you're curious, here is how a WASM module looks like. You can see it's a bunch of S expressions nested within one another. Definitely not something we want to call manually. And that's why headlines.js exists. So then our app is being served here. Let's try to open this up and take a look. And hey, looks like our app is running on the web. And notice we have a bit of repaint issue, but other than that, it seems to be working. So let's add the API key. And there you go, we have the headlines app running in the browser. But looks like the app is not loading the news articles at all. So let's debug that. And the reason is because we're calling fetch web, but we're not awaiting it at the call site. So I'm going to add await here. And let's try to build this again. And seems there is an error. So as it turns out, we'll again need an async block to be able to call await. But since fetchWeb is our top level async function, let's use an executor to execute this top level fetchWeb function. And for that, I'm going to add a crate called wasm-bindgen futures that can help us execute any async function within the web platform. So here I'm going to call wasm-bindgen futures, and I'm going to use the spawn local function. And to this, we can pass an async closure and put this within the closure. So with that added, let's take it for a spin. Let's add the API key. Okay, still no signs of any news articles being rendered here. Let's check our developer console. And it seems like we do receive logs here. So it turns out that the code we added here is actually handling the case when we have the API key already set and saved in the app. And if you take a look here, we haven't added the wasm specific code for this branch, which is the case when the user opens the app for the first time. So let's handle that case. Instead of a loop, we're going to use the setInterval API for the web platform. And this is again going to be behind the wasm target. I'm going to call the interval function, and I'm going to pass in 500 as the interval. And then we'll use a closure, and let's chain the interval call with forget so that it gets detached from the scope. And within this closure, we'll do the same app_rx receive. And if you receive the API key set message, we're going to call the fetch web function using spawn local, and we'll pass the clone of the API key and newsTX. Let's also handle the error case. We'll simply log the error message here, and let's take it for a spin. Let's add the API key. All right, there you go. We have our news articles being rendered here, and we can click any of the links and that opens up in the browser. But if I go back, you'll see that we're back to square one, and it seems like the API key was not really saved in the app. And that's because we're using confi here, which doesn't handle the case when we run on the web. So instead of using confi, we'll replace and use the built-in persistence feature in egree, and that will handle saving the app state on both the web and the native platform. So let's do that. So what I'll do is I'm going to go to, and I'm going to delete confi as the dependency. And then all I need to do is just take help from the compiler, and it would help me remove all the places where confi is being used. So I'm going to jump to 54 here in headlines.rs, and let's remove confi. Let's also remove it from the render config method. And then let's replace these with the default values, because we'll be initializing them using egree's persistence methods within the setup method. So with confi removed, let's go back to cargo.toml. And for iframe, I'm going to expand it to the object notation. I'm going to add a feature called persistence, and let's save this. Now with this added, we can then go back to lib.rs, and in the setup method, we can now use the storage param that gets passed to setup, and we'll use this to check if our app state has been loaded. So since this is an option, I'm going to do the iflet pattern match, and we're going to check if there is a storage object. We'll use the API module and call get value and pass the storage, and for the key we'll use headlines. And since the key might not exist, so I'm going to do unwrap or default, and we will assign the value to self.config. And then we'll also set the API key initialized field to be the inverse of API key is empty. So with this line, we will be trying to load our app state during the first render of the app. And in addition to this, we'll also need to override a method called save, and this gets passed the same storage object. And within this, we'll call the setValue method, and we'll pass the storage object. And for the key, we'll use the same key headlines, and for the value we'll pass the config object, and this needs a reference, so let's prefix with ampersand. And with this change, we should be saving our app state, and this is again a lifecycle method which will get invoked every once in a while during the lifecycle of the app, so we don't have to worry about explicitly handling saving the state of the app. So let's give it a spin once again. Let's enter the API key, and this works as expected. Let's open our developer console, and under the storage tab, let's go to local storage to see if the app key has been set. And as you just saw, the app key was set automatically. And then if we try to reload our app, we are no longer getting the render config window again. So the app state is being stored in the local storage now. But just a fair warning, even though we have local storage as a place to store any state that we want to persist across sessions, it's definitely not a good idea to be storing API keys in the browser's local storage. But since this is just for demonstration purposes, we should be good here. All right, so we are pretty much done here. But one additional change we can do is we can remove the close button, since it does not make sense when this is running in a browser. So let's go back to our code, and under headlines.rs, and to conditionally render the close button, we can use the config macro. And if it is not a wasm platform, we will then render the close button. And with that, the close button should go away. And there you go. So then I'll close it for today by implementing the solution for the exercise that I mentioned in the previous video, which was to add support for the refresh button. So to implement the refresh button feature that will reload list of articles, what we can do is we can use the aptx sender instance and send a refresh message to this channel. So let's do that. So I'm going to check if let some aptx. We're going to send a message called refresh. This variant does not exist, so let's create that. And this should only be sent when the refresh button is clicked. So let's put this within the click handler. And then let's go back to lib.rs. You can see we are already getting an error from the compiler that we're not handling the refresh case, which is the advantage of using a statically typed language. So we're going to handle the refresh message, and we're going to call fetch news here. Let's do the same for the wasm target. And here we'll call the fetch web within an executor. And just so we don't append to the existing list of articles, we're going to clear the current list of articles using the clear method. And also for a visual feedback, during the time when the articles are being loaded, we can simply render loading text widget. So I'm going to do if self.articles is empty. We'll then initialize a vertically centered justified container. And using the UI handle, I'm going to add a heading widget, which will contain the loading text. And let's put an hourglass emoji and end this with a semicolon. And in the else part, we're going to render the remaining of the widgets. So with that, our refresh button should be working and it should load the list of articles. And as you can see, while the fetch is being performed, we can see the loading state, and then we have the list of articles. And if I click on the refresh button, you can see that we can reload the articles now. And the one last fix we need to do is to fix the repaint issue. We'll need to render the config window within a container widget. So I'm going to go back to headlines.rs and in the render config method, I'm going to put window within a central panel. So let's do that. Let's call show, and within the closure, we're going to render the window object. And if I reload this now, great. So no more repaint issues there. Awesome. So that's how you build a web application in Rust. Now, although it seems that we did a lot of changes, but if you take a look at the UI code, most of it is unchanged. And we only needed to support a few platform-specific changes here and there. And this makes eGUI a very versatile platform. But just to be fair on using eGUI on the web is that there are a few downsides at the moment, and quite a few things don't work. But hopefully we'll get good support for them in future. I'll leave a link for this page if you want to read this in more detail. So yeah, I hope you learned something new, and hopefully this should give you some ideas on how you can build applications in Rust. Thank you for staying with me this far, and I'll see you in the next one.